Yeah, let's take a look here. There we go. Okay, so again, if you're just using the chain rule and applying the 5 as the coefficient of this function, right? The 5 just kind of comes along for the ride when you take the derivative of things, just like when you take the derivative of 5 times x to the third, right? The 5 just kind of travels along, and then we simplify it to this 15, right? And if that's the coefficient rule of a derivative, right? If the coefficient is multiplying a function, you either just find the derivative of said function and multiply it by the coefficient that you had to begin with, right? So that's this problem right here. And as Brian was asking, does it matter what order you put it in? And it doesn't, right? In multiplication, as long as you have them multiplying out together, it doesn't matter which one comes first, which one comes second. But please be careful. Do not write that. There's one thing I do need to note. Do not write that 6x inside the secant function, right? The secant function, what it has inside is only the 3x squared. The 6x needs to multiply outside of it. So just make sure you keep that in mind. So either one of these are fine. Now, if you say you did the product rule instead, and you showed that it was 5 times tangent of x, right? If you did the product rule for this one, you're not wrong. It's just extra work. Check this out. Oh, this is the derivative, I should say. So if I was doing the product rule and I said the first function was 5 and the second function was tangent of some stuff, right? The product rule states that it's the derivative of the first times the second plus the derivative of the second times the first. You got to know these rules, by the way. So derivative of f of x, derivative of 5 would just be 0, right? Times g of x, which is this stuff right here. But here's the thing. You don't care about this stuff right here because it's multiplying with 0. So this whole first thing goes away. That whole first thing disappears. Plus the derivative of the second. Derivative of the second, we found out it to be equal to derivative of the inside, which is 6x, times the derivative of the outside, which is secant squared of 3x squared. And then, of course, times the first function. And the first function is 5. Like so. So, like I said, this thing right here cancels out because it's multiplying by the 0. And I have here y prime is equal to 6x times secant squared of 3x squared times 5, which I don't know if you see it or not, but it's the same exact thing that I got with that first one with doing a little bit of extra work. Does that make sense? You see here, the 6x matches up with this 6x. This 5 is matching up with that 5, and then the secant squared of 3x squared is matching up with this one right here. So you get the same answer, right? And there's nothing wrong with doing the product rule for this one. I'm just letting you know that if you have a coefficient in front that's a constant, I'm repeating myself there. That's redundant, but I'm just saying if you notice there's a coefficient there and it's just a number, just bring it along. Just do the derivative of what's next to it and carry the other functions along with it, the derivative next to it. Anyways, that's your answer. Either one of these are acceptable. Like I said, I don't care if it's simplified unless it specifies it. If it tells you you need to simplify it, or if I was going to do a second derivative, then I would consider simplifying it. If it just said find the first derivative, I'm done there. I'm not going to keep going any further. But if you really wanted to, if you really want to clean it up, it would just look like this. 30x secant squared of 3x squared. And that would be your cleaned up answer if you were doing like a multiple choice answer or a second derivative. I would go to there and then take the second derivative. And this one, you cannot use the coefficient rule. This one, you have to use the product rule because that 30 now has an x with it. Okay? All right. That's number 1, guys. Hopefully you guys were okay with that. Hopefully that made a little bit more sense. I know some of you guys are, Brandon, you were asking for help. Does that make a little bit more sense, Brandon? Can you let me know? Is that easier to deal with? Or is that like, okay, good. Let's go on to the second one. Excuse me. Let's go on to the second one. Move that over a little bit so I have a little more space here. So, move this out of the way. Let's just go over there. Okay, so let's go over here to number 2. It's asked to find the derivative of this guy. This one, you have to use the product rule. You have to, right? You can't just take the derivative of this one and multiply it by its coefficient. It doesn't have a coefficient. It has another function multiplying with it. So you have to product rule this one, right? And like I was saying, the product rule tells you to take the derivative of the first multiplied by the second. So derivative of the first is 3x squared times the second, which is sine of 5x plus the derivative of the second. Now, the derivative of the second requires the chain rule because you have a inside of 5x and you have an outside of sine. And again, I'm going to slow it down there a little bit. Hopefully you guys understand or see where these guys are coming from, right? This right here, me breaking down the in and the out, is looking at just the second function, right? Because I need to take the derivative of that looking at the product rule. So I have here derivative of 5x d dx is equal to 5, and then the derivative of sine d dx is equal to cosine of some stuff. But again, what's that stuff? That stuff is this 5x that I'm dealing with. So derivative of the second function is equal to derivative of the inside, which is 5, times the derivative of the outside, which is cosine of 5x, multiplied with the first function, which is x cubed. And that's where I would leave it. That's where I would leave it. All right, so make sure you guys understand the breakdown of all of this, okay? This right here is the derivative, right, of the first times the second function. I'm not taking the derivative, I'm just multiplying it by the second. And then I find the derivative of the second and multiply it with the first. And that's pretty much it. Angela, I get this now. That's good, Angela. That's good. It takes practice, honestly. When you just look at all these things, it takes a lot of practice. And we're not even looking at quotient rule stuff, but I think a lot of you guys are comfortable with quotient rule because it's clear to see which function is which on there. But you can do it with combinations of all these. You can do chain rules with a quotient rule with a product rule in the numerator. Or you could do, and it gets all kinds of funky, and it looks complicated, but when you actually start working through it, you realize you're just applying the same rules repeatedly, right? Repeatedly. Now, if you want to clean this up and you want to simplify it, you can, but again, I encourage you to leave it alone. Where did I get the 5 in the second derivative? Okay, that's a good question. So the second function, right, is this entire thing, this sine of 5x. And what I need you to see is, if you ever have something like that, you have to see that that is a chain rule problem. You have a function, sine, and you have another function inside of that sine function, which is the 5x. That's where I get this whole in and out from. That sounds good, in and out. Now, the in function is 5x, the out function is sine. The chain rule specifies that if I have a function inside another function and I take the derivative of that, that just means that I take the derivative of the function we're dealing with, so the derivative of sine would be like this, for example, right? And then multiply it with the derivative of the inside function. And the derivative of 5x, Brandon, is 5. That's where I'm getting that 5 from. That's my long-winded speech for that. If it was, yeah, that's pretty much it. So that 5x, derivative of 5x is 5. So you take that 5 and you multiply it with the derivative of the outside function. Awesome. Awesome, no problem. You guys asking questions make it easier for me to understand what you guys need explained. If you don't ask questions, I just end up talking for hours. Well, not hours because I only have you for an hour, but I end up talking for an hour and it might not make any sense. And I'm not going to question it because I like the sound of my voice. It's soothing. I don't know, guys. I'm not making any sense. So let me just talk randomly. All right, so that's it. If you want to clean it up, that's as clean as it's going to get, right? 3x squared sine of 5x plus 5x cubed cosine of 5x. And if I asked you to take the second derivative, I would do it from here, and I would do the product rule for this one, plus the product rule for that one. But that seems like a fun problem, but we're not going to do that today. We're not going to do that today. Instead, today we're going to have to continue, right, with our lesson with using the chain rule to help us take derivatives of implicit forms, right? Implicit differentiation. And we're going to continue that today. So 3.2 continued, right? Kant. 3.2, let's see here, implicit. I spell implicit wrong, it's L-I, knock me. Differentiation, right, and this is continued. So where did we leave off last time for implicit differentiation? I think I did one example, and then I gave you the steps for it, right? So we're going to do another example, but before that, let me give you the steps for it first. So let me put that back on so you guys can have the steps for how we approach these types of problems. Okay, so let's take a look here. So when you're given something that's implicit, right? First things first, can you identify the difference between implicit and explicit? And if not, I don't know why I said that. I'm pretty sure you guys can. Something that's an explicit form is usually the form where it's explicitly in one terms of the variable. So like, for example, something that is explicit, I can spell, is usually of the form y is equal to x squared plus 3 tangent of x, right? It could be any complicated thing, but it's basically in a form where y is solved for. It's explicitly in one variable definition, right? Like it's defined as it's a dependent variable y, and it's dependent on only x and x only, nothing else. Implicit differentiation is when you have a mixture of the variables, and you can have 2, 3, but for our sake, we're just gonna be dealing with 2, right? If you guys decide to go into Calc 3, maybe you'll deal with 3 variables. Calc 3 is after BC, and that's what you take when you go off to college. And for anyone who's going into the STEM field, you're going to be taking Calc 3. In fact, you're probably going up to Calc 4. Yeah, most than likely. Anyways, I'm getting sidetracked. So let's take a look at an implicit one right now with only 2 variables, right? And that you can't solve for y, right? So let's do this example together, and we'll use this guideline to help us out here. We did one example last time, but let's start off with a new one today. Let's go with this one right here. Let's say I had here x squared plus xy squared minus y is equal to 7. And I was asked to find dy dx, right? So we're going to be doing this derivative here, but we're going to be doing it a little bit differently because I can't solve it explicitly. I cannot get y by itself. You see this? If I try to get y by itself, I have a y squared and a y there, and you'll factor it and you'll try to get it. You're not going to isolate this y, right? So we need to do it a different way. And that's where this guy comes in. That's where the implicit differentiation comes in. We take the derivative using these rules right here, these steps right here. So let's follow along here. First things first is to take the derivative of both sides with respect to x. Now, here's the thing. I've kind of been shortcutting this with you when you take the derivative of things explicitly, right? When you take the derivative of something explicitly, you guys would just write this down as y prime, or better yet, y prime, which is shorthand for dy dx, is equal to 2x plus 3 secant squared x, right? You would just write that out immediately and just say, oh, here, let's just ignore the 3 tangent x and just keep it simple with the x squared. You guys knew that the derivative of x squared would be 2x, right? But what I haven't been telling you is that you've actually been skipping on this little part right here. You've been skipping on what you've been taking the derivative with respect to. You guys might have seen me write it out, d dx, right? D dx is the notation that we use to tell us with what respect we're taking the derivative of, and it's with respect to x. Now, what does that mean? So if you want to think of it this way, when you do d dx of y, we end up with dy dx, right? And that y that's in here is the same y that's up here, but it's being attached with this d dx right there. So d dx of y is how we lead up to this dy dx. Now, why is that a big deal? It's actually being applied to the x's as well, guys, but it's with a chain rule. You ready for this? The derivative of x squared is 2x, right? That's the outside function. The inside function is this x, and it's supposed to be multiplied with the derivative of the inside function, which is dx dx. And again, where does that dx dx come from? It's the inside function of x that goes right there, which again, if I wrote that off on the side, it would look something like this: d dx of x. That's how that ends up being dx dx. Now, why haven't I been showing you this? It's, I'm not gonna lie, a little confusing. But it's there. It's been there this whole time. But you know why we don't write it is because dx dx, can you guys guess? Dx dx just cancels each other every single time. So when I take the derivative with respect to a variable of a variable that's the same one that I'm taking the derivative with respect to, the dx dx will always cancel out. And it doesn't even have to be x's. If I was doing it with respect to y's, then the y's would cancel out. right? You can do it for either one of those. Okay? So why am I bringing this up now? Well, here's what I need you to look at. When I take the derivative of x squared, it's technically 2x times the derivative of the inside, which is dx dx, but the dx dx cancel, right? Now, why do I bring this up? Well, when I start to take the derivative of things that have y's in them, right? The derivative of y squared, with respect to x, of course, is still going to equal to 2y, right? It's still going to equal to 2y. But you have to multiply it with the derivative of what's inside y squared. And what's inside y squared is just the y itself. And the derivative of y itself would be dy dx. And dy dx does not cancel. It does not cancel. The dy dx does not cancel. And it's actually going to be part of the problem now, right? So let's keep going here. Let me show you another one right here. So this is x times y squared. Please note, if I do this derivative right here, I can't just do the derivative of x multiplied with the derivative of y. This is x times y, right? When you have them written next to each other. So the rules when they're next to each other like this, I hope you guys see that it is the product rule that I have to apply here, right? Where x is my first function and y is my y squared is my second function. So I have to product rule this guy. So this is going to be plus, and let's get into it right here. It's going to be plus the derivative of the first function, which is 1, times the second function, which is y squared, plus the derivative of the second function. And this is where it gets tricky. The derivative of the second function is not just 2y. Derivative of the second function is not just 2y, but it's 2y dy dx. That's where I need you to pay attention and see that, right? The derivative of y squared is not just 2y, but it's 2y with the dy dx next to it, multiplying with it because of the chain rule. It's the derivative of y itself, the derivative of y itself with respect to x, with respect to x. Now this, of course, is multiplying with, don't forget, the first function, right? Now this is what I was saying. This is why I had you guys do that warm-up problem. You have to work your way through product rules and chain rules. And the chain rules seems complicated, but this is actually an easier chain rule because it's just y that's inside. And when you take the derivative of y with respect to x, you kind of just tack on the dy dx after it if you are anywhere lost on this type of problem. So are you guys lost? Or are you guys okay? You guys understand? You don't understand. I did the product rule there, and then I tacked on the dy dx when I was taking the derivative of that y squared. Okay, let's keep going here. Minus the derivative of just y by itself is just going to be 1 because derivative of x is just 1, but it'll be 1 times dy dx, right? The 1 is the derivative of that outside function, which is just y, and then the derivative of y itself is just dy dx. Now this is equal to, what's the derivative of 7? After we did all that, you guys should love doing the derivative of a constant, right? The derivative of a constant, derivative of 7. Doesn't matter with what respect you take it to, the derivative of a constant is just equal to 0. It's just equal to 0. Now that's a lot that we just went through, so I'm going to slow down a little bit right here and ask, are you guys okay with the 4 different things I've just written down? All right. If not, can you type it into the chat, right? Do you have a problem with part 1, part 2, part 3, or part 4? Is there any one of these things that you have a problem with? And you can just type in the number. Part 2, Max. Okay. Eric as well. And how did you get the -1 dy dx? So that's part 3, Brian. So let's go over those two things. Part 2 and part 3. Okay? Let's go over that. So not a problem, guys. Not a problem. So I'm going to work this off on the side. So part 2, right? The function that we're looking at is x times y squared. Okay, Eric? And Max, this right here, we consider that like our f function, okay? And this right here, we're going to consider like our g function. Since they're multiplying with each other, I need to, if I was taking the derivative of this guy with respect to x, I need to realize that it's one function multiplying with another function, so I need the product rule. And the product rule states this. I need the derivative of the first function times the second function plus the derivative of the second function times the first. Okay? Are you okay so far, guys? Hopefully you are. If not, please type into the chat at some point if I've lost you. Now, the derivative of x, which is in blue right there, is just equal to 1. Yeah, Eric's saying, okay, I get it. But Max, I'm going to still keep going for you, okay? And that's going to get multiplied with the second function, which is y squared. That's why I'm getting that part right there. Plus the derivative of the second function, which is this y squared right here. The derivative of y squared is 2y normally, right? It would just be 2y and we'd be done with it. But the problem is I'm taking it with respect to dx, right? With respect to x. So when I take the derivative of y with respect to x, not only is it 2y, but the derivative of the inside will spawn this dy dx for me. That's why it's not just 2y, but it's 2y dy dx. That's where that comes from. And that's just going to multiply with the first function of x. Yeah, right? That's where we get that from. Okay? So take a second there. I'm going to put it off to the side. And I want to go back over here now. Now, Brian's asking about how did I get the minus 1 dy dx? And that's coming from this guy right here. What's the derivative of that? Well, the minus sign is just the minus sign that's already there. So I put the minus sign down, right? Now, the derivative of y. Here's the thing. If I asked you, what's the derivative of x? Yeah, there you go, the exponent. If I asked you what's the derivative of x, it's x to the first. It would be 1, and we always stop there. You're not dumb, Brian. Brian. Yeah, you're not dumb, Brian. That's a perfectly valid question, right? Because I think we've been doing this whole time, and we always would just say, oh, it's just equal to 1. But it's technically 1 dx dx, and the dx dx cancels, and that's where this 1 is coming from. Hopefully that makes sense. All right. Sounds like that's the only questions I had. No one else typed in number 1, 2, 3, or 4. So hopefully you guys were able to be okay with that. So let's simplify this out, right? I know that in the past I told you guys, once you take the derivative, you don't have to simplify, right? But that's because it was already solved for when it was explicit. It was already solved for the derivative itself, right? When it was explicit, the dy dx came there and dy dx was solved for. I didn't care what was on the other side. In this particular case, dy dx is not solved for. Not only that, there's 2 of them, and that's not okay. I need the dy dx to be a singular thing, because that's when when you solve for something, it's always like, hey, solve for x. It was always x equals something, right? Hey, solve for y equals something. Hey, find the derivative. It's basically saying solve for dy dx. Tell me what is dy dx in this problem. And if I look at it, I can't tell you what it is just by looking at it. So we got to do some work, right? The dx cancels to a 1. So I'm going to rewrite this, and I'm going to try to simplify these parentheses because it looks like a headache if I just look at it like this. So I have here 2x plus 1 times y squared. I'm just going to write that as y squared. Hopefully you guys are okay. Plus 2y dy dx times x. I hope you guys are okay if I write that as 2xy dy dx. Now, if you write that as 2yx dy dx, that's not wrong either, right? As long as you write the variables like that. And if you write it as 2y dy dx, then x at the end, that's also not wrong. It's just simplicity's sake to keep like these single variables next to each other and the dy dx at the end, because that's what we're trying to get by itself. Minus 1 dy dx. And if you just write that as dy dx without the 1, that's perfectly fine as well. So then it's me cleaning it up. And so far, I've simplified step 1, which is to differentiate both sides with respect to x, right? With respect to x. That's step 1. Done. Step 2, collect all terms involving dy dx on the left side of the equation and move all other terms, meaning they don't have a dy dx, to the right side of the equation. This is a technique that you learned back in IM1, right? When you're solving, or IM2, I forget which IM it is, but when you're solving to get one thing solved for, you get it all on one side, and everything that doesn't have that one thing, get it on the other side, right? So I want all the dy dx's on one side and get everything that doesn't have a dy dx on the other side, which happens to only be the 2x and the y squared, right? That's the only thing that doesn't have a dy dx. Everything else gets to stay at this party. It's become exclusive only for dy dx's. So when you simplify this out, I end up with 2xy dy dx minus 1 dy dx equals to negative 2x minus y squared. Now, if you write it as minus y squared minus 2x, that works as well. A negative y squared minus 2x, if you want to write it that way, that works as well. But that's step 2. Done. Get all the dy dx's on one side, get everything else that doesn't have a dy dx on the other side algebraically. Step 3, factor a dy dx out of the side where you have them. Now this one says left side. So factoring a dy dx is just like factoring out a common factor of like a 3 or a 4 or a 9 or an x, right? You could, if you have multiple common factors, I'm only focusing on factoring out the dy dx. So I factor out the dy dx, I get here dy dx, and what's left behind is 2xy minus 1. 2xy minus 1. You guys okay? Factored it out, right? Factored it out. Now, once I factored it out, I'm going to go ahead and divide both sides by 2xy minus 1. 2xy minus 1. So when that was step 3. I factored it out. Step 4, divide both sides by the equation by the left-hand factor that does not contain dy dx. That's this guy right here. It does not contain the dy dx. I divide by it to the other side, and this cancels out on the left side, and I'm left with dy dx is equal to negative 2x minus y squared over 2xy minus 1. And that's your answer, right? And that's your answer. So implicit differentiation, right, looks complicated. I kid you not. I don't disagree with people who say this looks really weird, and it does. It does. But it's the same concept as what you were doing before. You're just trying to get a function that will tell you what is the slope of the tangent line at a specific point, right? And when you did it explicitly, you kind of just needed the x value, right? Once you get the x value, you figure out, oh, you plug that into that function and you'll see what the derivative is. Implicitly, you need two values. You need an x value and a y value. And once you get both of them, you can plug them in. I can plug in the x value here, and I can plug in the y value here, and figure out what is the slope of the tangent line at that point, because that's what the derivative does. What's the change in the y compared to the change in the x? And that's all this is. You're just calculating these derivatives just so you can get to this dy dx. Okay. I wanted to show you something real quick though before we move on. And again, don't worry if you don't get it off of this one or second example. We're going to do some more because this definitely takes practice, right? Takes a lot of practice. So let me I just want to show you this real quick. If you graph this onto Desmos, it knocked me with this Desmos. And yes, knock me with this Desmos is something that shows up a lot here. And I should actually technically be doing this on your TI calculator, but it's just easier on Desmos. Not to sound like I'm a spokesperson for Desmos or anything, but check this out. Here's what the graph of that function looks like. Can you explain that part again? Putting the derivative sign in front and multiplying or dividing. Okay, let me show you that first before I show you this sponsored by Desmos, according to Calvin. So the idea on this step, Brandon, right here, going from here to here and factoring out the dy dx, the idea behind that is, if you think back to it doesn't matter, your classes before. If I asked you to solve for x, and I gave you a problem that was something like this, it was like, let's say I was asking just to solve for x, and the problem was 20z squared x plus 5x is equal to 30, right? And I was trying to solve just for x, meaning I was trying to get x by itself. Since these guys both have an x term, I can factor out that x, right? Which is the undistributive property, right? So I can factor out that x in front. I get here x times 20z squared plus 5 is equal to 30. And if I'm just solving for x, I can get rid of this thing right here by dividing by this 20z squared plus 5 to the other side. And that gets my x by itself. You see that? And that's what I'm doing here. Instead of solving for x, though, I'm solving for this dy dx. And I'm dividing by what I have remaining when I factored out the dy dx. If I distributed the back in like so, I would go back up to this step. But I'm doing the opposite of distributing, which is to factor it out. Got it. Thanks. Sweet. All right. Back to my sponsor from Desmos. So check this out. All right. This is what the function looks like. I shouldn't say function because it's not actually a function because it doesn't pass the vertical line test. But it is an equation that has x's and y's, right? Now check this out. Before in the past, when I asked you to evaluate the derivative, you would say, oh, what's the x value? You plug in the x value and you get it, right? But here's my issue. If I tell you the x value, let's say it was -10, right? Let's say it was -10. Are you talking about the derivative? Are you talking about the tangent line that goes right here on the top side of -10? Or is it going down here on the bottom side of -10? So when you're calculating your slopes now, telling me that I'm trying to evaluate it at x equals to 10 is not enough. Is not enough. And you can actually see that in the equation. If I tell you, hey, find dy, wow, knock me. Find dy dx at x equals to -10. That's not enough, because all you're telling me is to plug in the values for x, and then you'll have to tell me, well, what's the y value? So you need both values. You need not only the x equals to -10, but you also need to tell me what y value you care about it at, because the graph now looks like this monstrosity right here. So at -10, you need to tell me, oh, it happens to be -10 and 3. Then you can evaluate it and tell me what the slope is. And by the way, if you plug in -10 and +3, which would be that point right there, it would be a negative value, right? You can see the slope of this tangent line would be negative. Whereas if you plugged in -10 and -3, you're going to get a positive value because you have a tangent line that is going up to the right as opposed to down and to the right. Anyways, a whole lot of stuff getting thrown at you, right? But major thing is calculating for dy dx. All right, like I said, let's do another problem, because honestly, it's like a lot, right? It's honestly a lot. Let's do another problem real quick. Let's take a look at another one. So let's see here. I have here, for example, let's say I was looking at 3y squared plus 6y equals to 4x squared. And I was asked to find dy dx. All right, so there's my equation. There's what I need to find. So let me make a copy of this. I know, I'm sorry, I'll put it back in a second. Ah, no, stop. There you go. Copy. I was gonna put the steps down here so it'll be easier to see. Whoop. There we go. So let's go ahead and put that over here to the side. Let's make it a little bit smaller so I can fit it onto the screen. That's good enough. So 4 steps to calculating dy dx. And I hope you guys can see this is implicit, right? It's not explicit. Do you guys see why it's implicit? Y is not solved for, right? Y is not solved for. We can't solve for y, actually. I mean, you could try to do it quadratically, but it's just going to be a pain when all I need to find is the derivative, and I have these steps to do it implicitly. Sorry, my leg is itchy, and I really shouldn't scratch, but it feels so good to scratch. Is the cold weather, the cold dry weather, is that 4? Yeah, that's a 4. Wait, which 4 are we like? Yeah, that's a 4. That's a 4x squared. Let me write that better. This cold, dry weather is making my skin like super dry. I should just put on lotion, but it feels so good to scratch. Anyways, random point. I hate cold weather. It's not bad, Ryan, right? Cold weather isn't bad. It's just, oh, I think I just made myself bleed. That's okay. The blood will work as a lotion, right? And then problem solved. My skin won't be dry anymore, and I won't be itchy. All right. Let's see here. What are we doing? That's not okay. That's fine, Calvin. What's the worst that can happen? I get an infection. I have to chop off my leg. Yeah, it'll be fine. All right. So, man said it'll work as a lotion. Well, it will, you know, right? Blood's a good lotion. All right, stop scratching. Jeez. All right. So, can you guys go ahead and start this off? Try this out. And I'll work along with you. But if you feel like you want to try it on your own, try it on your own. And then, actually, you know what? No, let's do this one together. And then I got one I want you guys to try onto the pair deck. Yeah, let's do that. Let's do this one together. And then I'll give you one more example for you guys to try on your own. So let's take the derivative of both sides of this equation with respect to x. By the way, you don't need to show this part of me drawing the brackets and putting the ddx there. I just like showing it just because it reminds me that I'm taking the derivative with respect to a specific variable. And yeah, give me 1 second. Hold on a second here. There we go. Okay, so the derivative of 3y squared. No product rule needed, right? No product rule needed. It is a coefficient of 3, and I hope you guys can see that the derivative of 3y squared is going to give me 6y. But don't forget this part. The derivative of y itself is dy dx. See that? Then I can move on to the next part. The derivative of 6y. It's going to be 6 times 1 times dy dx equals 8, right? X dx dx. I'll pause here for a second. I'm going to number these terms. This is going to be the first term. This is the second term. This is the third term. And I'm going to pause. Does anyone have any questions on any of these terms that I have written down? How did I get term 1, term 2, or term 3? Can you guys type into the chat if you guys have any questions right now before I move on? Is it dx dx because it is a x value? Brandon, that is spot on. That is exactly it. And we just haven't been writing it, Brandon, because it's unnecessary. Dx dx is going to cancel out anyways. But I'm writing it now, and you don't have to write this down now, but I'm writing it down now just so hopefully it will help you to see where the dy dx is coming from, right? That's the connection between that. And it has to deal with what variables you're using, with what respect you're taking the derivative to. Okay? But it looks kind of quiet. No one's saying anything about 1, 2, or 3, so it seems like you guys are okay with that. So I'm going to move on, okay? So I'm going to move on here. That was step 1, differentiate both sides. Step 2, collect all dy dx terms on one side and everything else that doesn't have a dy dx on the other. Dy dx's are both on the left-hand side, and I have a dx dx on the right-hand side that doesn't have a dy dx, so step 2 is done. Step 3, factor out a dy dx from the left side of the equation. So when I factor out that guy and that guy, it's going to come out as dy dx. What's left behind is 6y plus 6 is equal to 8x. Now that's step 3, factored out. Step 4, divide from both sides of the equation by the left-hand factor that does not contain dy dx, which is this 6y plus 6 part. I'm going to divide to both sides like so. And I end up with dy dx is equal to 8x over 6y plus 6. And if you're one of those people who love simplifying things because you want to, please make sure you simplify correctly. This all has a factor of 2. You could rewrite this as 4x over 3y plus 3. But I would prefer it like that. But if you want to factor out, you can. And that's step 4. And that's your answer. Ooh, caught my pen. And that's your answer. How do you feel? You okay? You not okay? You want to cry? You want to pray to a different God because you don't know why this God would ever give a problem like this to you? How do you feel, guys? You feel all right? I think you feel all right. I think you guys are okay with this. It's hard to tell because, internet. But in my mind, I think you guys get this. I feel like you do. But let's hear. I got enough time for you guys to try one on your own. We got about 11 minutes. I want you to try one problem here, and I want you to put it into the Pear Deck. And let me see if you guys are able to calculate the derivative implicitly. Okay, and then next time when we meet on Thursday, we'll do more complicated ones where we have to do it implicitly with the product rule, with the quotient rule, with the other rules and whatnot, and then start to evaluate them. But we'll do that next time. This time, though, I'm going to clear, if you have the Pear Deck link still open, if you could, I'm going to go ahead and change the slide. Whoa, my Pear Deck just crashed. There it goes. I'm going to change the slide on there. Okay. So let's go ahead and switch the slide over. If you guys still need the link because you closed it, that's okay. I'm going to re-put it back in, and if you log in with your name, it should be fine. So here we go. There's nothing on the Pear Deck right now because I'm going to put the problem onto here. Okay, here's the problem I want you guys to try. try it on this pair deck. So here we go. I want you to find dy dx of, I don't need the of, find dy dx, and the equation is going to be 5x to the fourth plus 3y squared, and this is equal to y. So go ahead. Can you guys try that real quick? Let's go about 5 minutes, see where you guys are at for this problem. And if you don't know how to do it all the way, that's fine. Just start off with step 1 for me. Take the derivative with respect to x. That's step 1. Step 2, right? You can see if you're comfortable with it, and you could try that along as well. So let me put that right here. Go ahead and get on it, guys. Let's go ahead and try this out. I'll put that right there and put this right here. There you go. So try this out, guys. There you go. I'm going to go ahead and set a timer so then we can get started after the timer goes. Where's my thing? All right. Let's see here. Boom. There we go. Got the timer going. That's awesome. There we go. All right, guys. At the same time, I need to talk to you guys. I'm sorry I haven't graded your test from last week yet. Has it been last week or 2 weeks now? Just been really bombarded with a lot of different things. Good news, though, I passed my online class. I don't know if I told you guys I'm taking an online class to better my education. Yeah, yay, class, yeah. So I've already started up on the next class already, and yeah, I got to get on that. And I'll get your test scores graded and calculated, and your curves graded and calculated. Your last progress report is, oh, thanks guys, I appreciate that. But your last progress report is this Friday, so I want to get you an up-to-date progress report for you, because I know that some of you guys are worried about your grades, and your final grade is going to be in December, right before we go on Christmas break. I'm sorry, winter break, right? So December 18th is the last day that you can do work that counts towards your finalized grade for first semester. So I want to get you an idea of what your grades are by the end of this week, so you can see what you need to do for the next test and the final, right? What you need to do for the next test and the final, and then that grade will be there and locked in by that day. Other than that, though, what else is there? I think from what I saw, there was a good amount of you that did the curve, so that made me feel good about it. This chapter right here that we're on, this chapter 3, I'm put 3 in quotes because it's not actually a full chapter, is relatively quick. Like the big part of it is this implicit differentiation and the chain rule. Once we get past that, the next couple of topics will fly by really quick because they're just small things that need to be covered, and then they don't fit anywhere else, so we'll just throw it into here. But this test will look a lot like, and when you take it, you're going to realize it looks a lot like your last test, except now we're going to be applying the chain rule and implicit differentiation. And I just want you to know, like, I don't want you to stress out over this, but if you were struggling in Unit 2, at this point, I really need you to start coming to see me, and we can do some of your homework problems together. It will help. That's all I can tell you is derivatives seem complicated, but it's one of those things that if you just do it repeatedly, you actually will get better at this. You actually will get better at this. It's one of the weird ones, though, but it just takes a little bit more practice. Okay? Anyways, let me see here. How are we on time? We got about a minute left, and you guys are looking good. You guys are looking good so far. Looking good so far. So let's go ahead. I'll put the timer over here. We got about 40 seconds or so. Let's extend it a little bit more. You guys are looking good, but you're at a certain specific step. So let's add to that. Let's make it another minute on top of it. You guys are looking good on these. Not bad. Some of you guys already just have the answer. Kaylee, that is awesome. Oscar, that is awesome. Good job. Keep going, Ava. Keep going. Max looks good. David, thank you. I appreciate that. Nice drawing and also nice answer. Let's see here. Brian, still working on it? Then look, that looks good. What you have so far looks good. So keep going. Oh, both Brian's. Yeah, it looks good. Monica, awesome, awesome. I think that's right. Emily, beautiful first step. That what you have written down there is beautiful. Just one little thing. The 20x cubed, is that a dx or is that a dy dx? Be careful with that. It looks like a dy dx, which you might not need there because it's an x function that you're taking the derivative with respect to x to. Leslie, looks good for your answer there. Calvin. Oh, you're so close, Calvin. You're so close. Remember, the derivative of y, Calvin, is not just 1. The derivative of y with respect to x is 1 dy dx. So keep that in mind. All right. I want to see a couple more here before I have to go. Jeffrey, so that's it. That's the good derivative there. You got the dx. That's beautiful. And you're at the 6y. Don't forget the derivative of y, right? 3y squared is going to come out to be 6y, but don't forget to add on the dy dx at the end of that as well, right? Same thing, Diana. I think you missed on the derivative of y. The derivative of y is 1, but don't forget the inside part, which is going to be 1 times dy dx. Don't forget that part. I think that's a common mistake. Yeah, a couple of you made that right there. So let's take a look at this problem before we got to call it a day here. Let me move you out the way. Move out the way. So let's go ahead. Take the derivative of both sides with respect to x. Right? That's what the d dx is. I'm taking the derivative with respect to x, and I have here 5x to the fourth is going to give me 20x to the third. And again, you don't have to write this part because the x matches with this x right here, but I'm just going to show you the idea of taking the derivative with respect to a variable gives you a dx dx. And this x right here is coming from the fact that I'm taking the derivative of that guy, right? And then you do the same thing for the next one. Derivative of 3y squared is 6y, but it's also multiplying with dy dx. And why is it multiplying with dy dx? Is because of this guy right here being the derivative of that with respect to x, right? We're going to keep going here. And the derivative of y itself is 1. But again, it's not just 1 by itself. It's 1 dy dx. And again, y is this y. That's all it is. That dy is coming from the fact that it's d right there, right? And I hope you guys can see that. Like if you're looking at that dy dx right there, the one that I have in blue, the idea is that you're taking the derivative with respect to x of y, right? The derivative of f, derivative with respect to x of y, and that's where that's coming from. Okay, so that's step 1, differentiate both sides. Step 2, get all the things that have dy dx on one side and all the things that don't have a dy dx on the other side. So 6y dy dx, that's good. I'm going to leave it on the left-hand side right here. 6y dy dx. I'm going to subtract the 1 over because that 1 has a dy dx with it. And then I'm going to move the 20x cubed to the other side. But of course, it's supposed to be 20x cubed dx dx, but the dx cancels out. Factor out the dy dx. I'm left with 6y minus 1 is equal to 20x cubed. Divide both sides by that 6y minus 1. And then you are done with this. You get dy dx is equal to 20x cubed over 6y minus 1. And that is going to be your answer. And look at that, I stopped. Wouldn't the, yes, that is negative. Did I not write negative? Look at that. Max, Monica, and Brandon catching my examples. Oh, okay. It's okay, we just ended class. It's 10:37. Good job, Brandon, Monica, and Max, for catching that mistake. I appreciate that. And that's perfect time to end this at 10:37 today. I'll put up some more practice problems. It'll be considered homework, but you won't be able to do all of them yet, but it's a good way to start. All right? So we'll do some more on Thursday, guys. That's it for me today. Have a good rest of your day. I'll see you guys on Thursday, all right? So long, guys. Thanks for hanging out with me today. Whoops. Have a good day. Bye, guys. Bye, everybody. Woo.